So in this video, we'll be discussing periodic trends in atomic radius, ionization energies, and electronegativity. Discussed in detail the definitions last time and majority of the trends. But now today we're going to just finalize what the examiner needs to ask you and you need to answer. But before we do that, I'd like to talk about atomic radius and the various ways in one which can measure the atomic radius. The radius implying that the size of this would represent the size of the atom, and for each different type of particle there's a different kind of radius that we measure. For metals we measure metallic radius. For non-metals we tend to measure either the covalent radius or van der Waals radius, and for many both exist, but only for some only the van der Waals radius is the one that's measurable, and we discuss all kinds right now. So let's start with the metallic radius and what that means. Now, metallic radius is the way we've defined the radius of atoms of metals. Those guys that are found as metals at room temperature, things like calcium, potassium, sodium, and all those. And by technical definition, it is defined as 1/2 of the distance between the two adjacent metal ions in a metallic structure. Now, for that, I'm going to show you the layout of any metal. So imagine you got a metallic lattice here. Now imagine these guys to be, let's say, Mg2 plus ions. So metallic radius is basically the distance between the center of these two nuclei. And let's see if I can mark them with a different color. Let's say here and here. So you take this distance and you divide the distance by 2. So this distance from the center of the nucleus to the outer, to the half of this distance is defined as a metallic radius. Now this is by definition is defined, and we not want to worry too much about why this is a definition. I'd love to get into half an hour discussion on all these three, but just the basic idea that is defined as the distance between the two nuclei in a metallic lattice. Understand that in a metallic lattice, these guys are already cations. So this is, each of these orange circles represents Mg2 plus. So it's not really a pure atom, it's an ion, but it's an ion, and it's the distance between the two ions, and then you've got to see some extra space also here. So there's a flaw in this measurement, but we will work with that flaw. So by calling a metallic radius, we are identifying that yes, we have this flaw and we work with that. Now, so for all metals, especially the ones that we're going to talk about in group period 3, because we're really going to focus on period 3, those exist for sodium, magnesium, and aluminum. So these guys, the atomic radius is defined as the metallic radius because they are found as metals at room temperature. Now, for elements like phosphorus, sulfur, chlorine, we're going to talk about their covalent radius because these guys make covalent compounds. So what we can do is explain to you what their measurements are. Imagine you have a molecule of chlorine that look like this somehow. So technically speaking, covalent radius is half of the internuclear distance, meaning the distance between two nuclei in singly bonded atoms in a molecule. So between two singly bonded atoms, what I mean is this, that if this is the nucleus for one and this is the nucleus for the other, you take this distance and you divide that by 2. And so this region or this distance is the covalent radius. Now obviously you can see there's an overlap between the two. Now this represents the atom. I should tell you that this blue is 2 atoms of chlorine overlapping each other, and these are the 2 nuclei, and their distance divided by 2 is the covalent radius. Now that's how we define the radius to be covalent radius. It is a distance between the 2 nuclei in a molecule where there's only 2 atoms singly bonded. That would be the covalent radius of chlorine. Now that's how we get the radius of all non-metals except for group noble gases, because the noble gases don't covalently bond. So the only thing we can really do is to find the distances between their atoms, but they're not held by covalent bonds, they're held by van der Waals forces. So hence their definition is van der Waals, and the difference is that their atoms are not overlapping like this. Let me show you the atoms of, for example, argon. Now here I'm going to show you 3 atoms of argon right there. So for argon, the van der Waals radius is defined as the distance between the two nuclei in two van der Waals bonded atoms, because they don't have covalent bonds. So you can get them as close as possible, and because the force of attraction holding them together is van der Waals, it's called van der Waals radius. And what you're doing is you're taking basically the distance between two nuclei and dividing it by 2. And the problem with this, and this is going to come in handy when you're going to understand the radii, is that this versus this is a flawed measurement. Now what you get here is that the measured value of this radius in covalent radius is, this value is smaller than the actual radius, because there's overlap, and overlap makes the distance between the two nuclei less than the diameter. While here there is no overlap. In fact, there is distances because they really can't get close to each other, too close, because the forces are not overlapping. So this distance that you're dividing by 2 is actually greater than the radius. So the measured value for argon's radius, so basically argon's measured radius, and this is a problem, for example, in period 3, because the reason why we're doing period 3 is period 3 starts from sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. So group 1, 2, 3, 4, 5, 6, 7, 8. Now compared to all the other non-metals, this guy measured radius is greater than the expected value, because the reason is that the measurement is flawed and you're going to get a larger measurement than the actual value. While for all covalent radius, the covalent radius for anything doesn't have to be argon, are always going to be less than the expected value. Okay? And the idea is that, and the reason for that is they're overlapping. So these values, the ones that you measure, the ones that exist in the data booklet, are smaller than the expected value, while the van der Waals radius for anything, argon or any other group 8, that radius is greater than the expected value. And when we talk about trends, we talk about expected values. And what you remember from last class was that when we had done atomic radius, we had studied that across a period. So what happens across a period for the radius is, across the period the atomic radius should decrease, and that's important. It decreases, and by that, and the reason why it decreases is because across a period, across these guys, the shells remain the same. The nuclear charge goes from 11 plus, 12 plus, 13 plus, 14, 15 plus, 16 plus, 17 plus, 18 plus. So as nuclear charge increases and the shielding remains the same, because the shells remain the same, the attraction for the outermost electron increases, so the size would decrease. And that's what we see, the size decreasing. And so when you're plotting even the trends, and generally you might say, you know what, let me make a graph trend for the radii, and you start from sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. And if you want to make the atomic radius, the trend looks like this. It decreases from sodium all the way to chlorine. And our argon's radius is supposed to be less than that of chlorine. The problem is the measurement. So this should go down and get a value here. But the problem is that the measurement is flawed for argon. So, this goes to chlorine. And after chlorine is supposed to decrease to argon. And that's what happens as a trend. But if you look at data booklet values, argon's data booklet value is even greater than that of sodium's. And for that, and the reason for that is that the value is flawed. So if you're looking at trends, and all MCQs will be based on trends, then you should realize that argon is smaller than everything else before it. Because across these 8 guys, the nuclear charge is increasing from 11 plus to 12 plus to 13 plus, all the way down to 18 plus. And they all have 3 shells. So shells remain the same, shielding remains the same, but the nuclear charge decreases, so size should decrease. So argon is smallest compared to everybody else. But if they ask you to sketch using data booklet values, the data booklet values are from basically flawed data. So you need to realize that the data booklet value for argon is greater. But in reality, it should be smallest, because that's what the trend says. The fact is that we don't have a way to measure it. So the measurement is flawed, that's why the value is greater. But all the values decrease across a period. All atomic radius values decrease across a period. And that's something that you got to remember. Now we also have got to talk about atomic radius down a group. For that, we'll go to the next slide, take a blank slide. So So here we're discussing atomic radius and its trends down a group, and we've discussed this on the last video also, but let me reiterate. The down a group, atomic radius will increase, and the increase happens because as you go down a group, the number of electron shells increase. Even though, let's say, look here, if you've got group 1, you go from lithium to sodium to potassium, and you're going from 3 protons in lithium to 11 protons in sodium to 19 protons in potassium, and obviously there's greater nuclear charge in potassium for the outermost electrons, but because there are more shells, there's more shielding and therefore more repulsion between electrons, and that outweighs the increase in nuclear charge. So as you go down, the atoms get larger. The same trend is seen in groups 1 and group 7. Down the group, the size of the atom increases. Okay, so down the group, size of the atoms increases. And just to repeat that and put it to rest is that across a period, atomic radius decreases. You are to be able to draw these 3 sketches for a metal key. Down the group increases, and across a period, especially period 3, the size decreases. And that's the trends for atomic radius across a period. On the next slide, let's talk about the trends for ionic radii. Okay, so now let's discuss ionic radii. Now, there's different trends for cations and different trends for anions. And what are cations? Cations are basically atoms when they lose electrons to become positive ions. Now, first of all, we got to discuss how the elements like sodium size versus its ion, or magnesium size versus its stable 2+ ion. And for that, we'll also discuss its 1+ ion, even though it's not stable, just to understand what's happening to the sizes. And then we will discuss obviously the anions too, but even in the cations, we can discuss the trends with multiple cations of multiple atoms in the same period. We'll have to look at that trend also. So let's start off with discussing how does the size, for example, of magnesium vary with that of magnesium plus and magnesium 2+. So why would there be a change in size going from magnesium to losing electrons to M+ to M2+? The most obvious answer is when sodium loses 1 electron, it's from its outermost shell. When magnesium loses 2 electrons from its outermost shell, both of these will have 1 less shell. But we're going to look a little deeper into that, because even when magnesium goes from magnesium to magnesium 1+ to magnesium 2+, there is a decrease in size. And that I'm just going to show you with the diagram showing the atoms of magnesium and then explain to you why that happens. So scrolling down to this diagram here, I'm using this to represent the 3 particles of magnesium, the atom of magnesium and the 1+ ion and the 2+ ion. And what I'm trying to show you here is that the sizes are decreasing. Even on losing 1 electron, the size is smaller than the atom, and on losing 2 electrons, the size is even smaller. Now, why does this happen? The reason why, to explain that, the reason why I put this ion in there is to explain to you an idea that, like, the most obvious answer for going from magnesium to magnesium 2+ is that magnesium has 3 shells, 2, 8, and 2, but magnesium 2+ only has 2 shells, has 1 less shell, so obviously it'll be smaller. But what you got to understand also is that even on losing 1 electron and maintaining the same number of shells as 3, the size of magnesium 1+ is also smaller. And the reason why it's smaller is because in both cases, the outermost electron is being pulled by the nucleus. Now, the difference is when it loses 1 electron, when let's say it loses this electron, what's happening is there are only remaining 11 left here. And the 11 electrons are repelling each other. The total repulsion of those 11 electrons is less amongst each other than those with the 12 in the previous case. So when the repulsion is less in this particular case, so the net attraction by the nucleus becomes greater. When that becomes greater, the electrons are pulled closer to the nucleus. So what's happening here is that every cation, and this is true for all cations regardless of losing all the outermost electrons or no, and that is that when you lose any 1 electron, there are fewer electrons remaining. Now, if there were 12 electrons here, there are 11 electrons here, and in magnesium 2+ there are 10. So for the same nuclear charge, 12+, 12+, 12+, as you go from Mg to Mg1+, you are pulling in fewer electrons. So unke aapas mein they have got less repulsion. When they have less repulsion, they have greater attraction by the nucleus, and the size decreases. So Mg2+ is even smaller for 2 reasons. One, Mg2+ has fewer electrons than the Mg atom, so the repulsion is less, so the attraction for the cloud is more. And the second reason is that all the outer electrons from the 3rd shell are lost, so you only have 2 shells left. So there are 2 reasons why a cation while many cations are smaller than the atom, but not always, because in transition metals, you don't always lose the outermost electrons, all of them. But even there, the cations are smaller because every time you make a cation, you have fewer electrons. And if you have fewer electrons, their repulsion is less and their attraction is more. So that's why the size decreases. So the radius of cation is always going to be smaller than the radius of the atom. And for that reason, please understand the radius of cations are smaller than the radius of the atom. Now, it's not just that we'll discuss this, but we got to also talk about that in period 3, you got, when we're discussing things like sodium, magnesium, and aluminum, as atoms, we knew that 11 protons pulling 11 electrons, magnesium was 12 protons pulling in 12 electrons, and aluminum was 13 protons pulling in 13 electrons. And so across this, the shells remained the same, the nuclear charge increased, so size would decrease. But we don't just discuss them, we also should be able to compare the ions of each of these, like sodium versus Mg2 plus versus Al3 plus, the naturally occurring ions. All of these three, we call them isoelectronic particles, and the reason why they're isoelectronic is because even though they have different number of protons, when you lose the outermost electrons, you got inner electrons left, and for all these three from period 3, the inner electrons are 10, so they're isoelectronic. And because they're isoelectronic, the repulsions remain the same amongst each other. But their nuclear charge is increasing, going from 11 plus, 12 plus to 13 plus. So in Al3 plus, the 10 electrons are being pulled much more strongly by 13 protons versus the 12 or the 11. So here what you see is, again, between these three particles, if they're isoelectronic, the electrons are the same. So the size depends on the nuclear charge. The greater the nuclear charge, the smaller the ion. So magnesium is going to be smaller, magnesium ion is smaller than magnesium atom, and also it is going to be smaller than sodium, and aluminum 3 plus will be smaller than magnesium 2 plus. So graphically, this is how you could probably see this. Like, first of all, simply speaking, if I were to make a basic sketch, and knowing that if I'm just making these three, sodium, magnesium, just these three, and so as atoms, let's say I'm a yellow line for the atoms, across the period size will decrease. Now it's be like this maybe. Now they're individual ions. The sodium's ion will be smaller than sodium, and magnesium's ion will be smaller than magnesium, and aluminum is smaller than aluminum, and these three will also decrease. I'll make a better line like that, So they're the cation, they're the atoms, and these are the cations. Atoms and the cations. The cations are smaller than the atoms. And within the cations, they have the same number of electrons, but as you go across, the nuclear charge increases, so the size should decrease. Okay, scrolling down, I'm going to show you the sizes of group 1 atoms and ions. So the solid line is group 1 atoms, and down the group the size increases. And then you got the group 1 ions, and the ions are smaller than the atoms because there are fewer electrons than the protons, so the attraction is more. There's also one less shell, but as even within them, obviously the size will increase because then the guy below it will have more shells, and that will outweigh the increase in nuclear charge. The same trend for the atoms. So the cations are smaller than the atom, and down the group the atom size increases. Okay. Now, we look at some anions and then talk about the whole period. So, what's the trend for anions? Okay, so now looking at anions, what we know is that the radius of anions are basically, for anions, are greater than the radius of the atoms. Now, let's take the example of chlorine. Now, the chloride anion versus the chlorine atom. Both of them are being pulled by 17 protons. But the chloride anion has 18 electrons while the chlorine atom has 17 electrons. So the anions will always have more electrons than the number of protons. And because there are more electrons in the anion, even from the atom itself, there'll be more repulsion between the electrons. And if there's more repulsion between the electrons, for the same nuclear charge, the repulsion is more, so the attraction will be less, and therefore the ion will be larger because there's more repulsion than the atom. So all anions are larger than the corresponding atoms, and that's true for not just for 1 plus ions, but you can also do it for 2 minus ions. Sorry, not 1 minus 2. sulfides are greater than the sulfur. The phosphides are greater than the size of the phosphorus atom. And this is something that you'll have to put together for all of period 3. So let's put it all together now, and I'll just show you the graph for that. Scrolling below. Now these are the sizes of the atom and the ions. Now the white line in the middle is the size of the atoms down a group in period, across a period in period 3. From sodium across a period, the size will decrease. And the blue lines are the size of the cations and the anions. The corresponding cations are smaller than the atoms, and the anions are larger than the corresponding atoms. And you should be able to sketch the graph for atoms, atomic radius, and the cation and the anion radius. Now the beauty is that all of these 4 cations, silicon can make a 4 plus and a 4 minus ion. So if I'm comparing the 4 plus atom, 4 plus ion, remember these are all isoelectronic. That means the number of protons might be increasing from 11 to 14, but all of these 4 have 10 electrons. While the guys on top, the anions, have 18 electrons, and you go from 15 protons to 16 protons. From silicon is 14 protons to phosphorus is 15 protons to 16 protons to 17 protons. So across even these guys, the number of protons are increasing, but the electrons are remaining the same. And between them and the elements, the anions are larger, and between the atoms and the cations are smaller. So that's important. And what you will realize is that the previous period's atoms will be close enough to these guys versus them, because the previous period's atoms also have 2 shells, and these guys have 2 shells, while the anions have 3 shells. So you'll have to be able to sketch this graph for atomic radius and ionic radius for period 3. After this, we will be looking at the trends of first ionization energies across a period. So on the next slide, I'm going to show you the graph and the basic idea. Now, first ionization energies across period 3. This is what we're going to study, and they're indicative of any period. But period 3 padhte hain because syllabus says period 3. And there's a general trend to it. And the general trend for ionization energies across a period, and we have actually discussed this in the previous video in detailed explanation, is that across a period, the nuclear charge is going to increase, and the shielding effect remains constant, mostly, not always, but let's say for now, that's why it's called a general trend. We'll talk about specifics in a second, but the shielding effect mostly remains constant. And because of that, the attraction for the outermost electron will increase, therefore more energy required to remove it. Therefore, across a period, first ionization energies will increase. Now, that means that if I'm looking at a general trend graph of first IE from sodium all the way to argon, the general trend should increase, and it does increase for first ionization energy. But what we find is there are a couple of places where it hicks up, where there are changes, and those changes are at aluminum and at sulfur. And that's why the graph that I'm going to show you right now differs from this one. It's not just the graph of period 2 versus period 3, though please understand that a period 2, period 3 graph for first ionization energies looks almost the same, and I'll show that to you also. But I couldn't find a period 3 graph from any book, and this was just nicer. I just used this one. But it holds true for period 3 also. And what you see is across any period, ionization energies are increasing, except for a couple of places it dips. And it dips when the elements are going from group 2 to group 3, and group 5, or now called 15, to group 6, now called 16. It doesn't just happen in period 2, it happens in period 3 also. And that's why I'm going to show you all the graphs for period 2 and period 3 all put together in one place. And then we'll discuss these dips, this one and this one in specificity. Here we have the first period, this second period, and a third period. Forget all these words for now. Just focus on these graphs, and I'm just going to highlight them. This one for period 2 and this one for period 3. And what you realize is going from group 1 to 3 is a dip, 4, 5, 6 is a dip, 7, 8. Then all the way down to group 1, 2, 3 is a dip, 4, 5, 6 is a dip, 7, 8. If this dips didn't exist, everything else is perfect, because across the period it will increase, and then suddenly in the next period When there's a down the group, it will decrease. That's why lithium is more than sodium, which is more than potassium, because down the group, ionization energies are decreasing. It's true for group 1, it's true for group 8 noble gases. See, down the group. But across a period, they are increasing. But there are a couple of dips, and the dips are the same. The reasons are the same for period 2 and period 3. So now let's focus on the period 3 graph. I'll show you on the next slide. So you're gonna pause, the next slide coming up. Okay, so here we have a graph of just specifically the ionization energies, the first ionization energies of period 3. And as a general trend, the values are increasing, going from sodium, magnesium, aluminum, silicon, phosphorus, chlorine, and argon. They're increasing. I've made the electron box diagrams. I'll talk about that in a second, but the general trend is increasing. Except for going from magnesium to aluminum, it decreases, and phosphorus to sulfur, it decreases. So let's talk about the general trend. Why is it increasing? It's increasing because across a period, the nuclear charge is increasing. Sodium is 11 plus, magnesium is 12 plus, aluminum is 13 plus, 14 plus, sulfur, phosphorus 15, sulfur 16, chlorine 17, and argon 18. So across a period, nuclear charge is increasing, the number of shells remain the same, so the outermost electrons are getting attracted more, which means it's harder to be removed. It's harder to remove them. Therefore, more energy required to remove them. Therefore, ionization energies increase. And that's the reason why magnesium is higher than sodium, or silicon higher than aluminum. Why is the next guy higher than the previous guy? Except for the two places where it's not, because something else is happening here and something else is happening here. Now, what is happening here? Why is the ionization energy for aluminum lower than that for magnesium? For uske liye, you need to understand that what's happening going from magnesium to aluminum. In magnesium, when you want to lose the outermost electron, that electron is residing in the 3s orbital. And that guy is only being shielded by the 1s and the 2s and the 2p. While in aluminum, if you want to remove the outermost electron, you're not removing it from the 3s, because aluminum is not just 1s2, 2s2, 2p6, 3s. It's also 3p1. So this is the configuration of aluminum. And the extreme outermost electron is the 3p1. And that guy is not just slightly further away, it's also shielded more, because in addition to the shielding that's common with magnesium and aluminum, both have the same shells that shield. In aluminum, the outermost is also additionally shielded by the 3s. And that fella makes the attraction for this guy lesser, which makes it easier for this to be lost. Now here I'm going to show you the atoms, a representation of the atoms of magnesium and aluminum, so you get an idea of what's happening. So let me scroll down, and here I'm going to show you the 3 atoms. This is a representation of the 3 atoms we're talking about, starting from sodium to magnesium to aluminum. Now, just from sodium to magnesium, I have not drawn the inner electrons to make it simpler, just the shells. And the outermost in sodium, that guy, the pink one, is being pulled by an 11 plus nucleus, and that is going through 2 shells of shielding. So now comparing that to the guy in magnesium, that's being pulled by a 12 plus. So greater attraction going through the same number of shells. So the shielding effect is the same in both cases. Hence, this electron is being pulled more, therefore harder to remove. Therefore, more ionization energy required for this electron than for this one. But from going from magnesium to aluminum, which is drawn here, I have not just drawn the 2 shells, I've also drawn the s and the p orbitals on the last shell. And the reason for that is that when I'm trying to remove the outermost electron from aluminum, it's not the s electrons, it's the p electrons. So this fella right here, 3p1, and that electron is being pulled by the nucleus. The nucleus is in this case 13 plus. So you'd say more attraction, but what you also need to account for is that while attracting this, it's not just going through the first and the second shells, it's also going through the 3s of the third shell. And that 3s that I'm highlighting right now, that is providing extra shielding between the outermost and the shell, and the nucleus. And so this 3p electron is being shielded in addition to what it already is in in sodium and magnesium. But this guy is also being shielded by the 3s electrons. So it experiences additional shielding by the 3s. Therefore, its attraction is less. Therefore, less energy required to remove it, which is why aluminum's first IEE is smaller than that of magnesium. But anybody after aluminum also has the same shielding as aluminums. So aluminum के बाद जो element आता है वो silicon, that will require more energy than aluminum, because between aluminum and silicon everything else is the same, but silicon has a greater nuclear charge. So I'm going to go back to the graph and talk about that for a second. So aluminum, less energy because the electron is 3p and has additional shielding from the 3s orbitals from the same shell, therefore less energy required, and that overcomes any increase in nuclear charge, hence the ionization energy is less. And every element after that has the same problem as aluminums, the additional 3s shielding. So in दोनों में फर्क नहीं है shielding का, but this one has a greater nuclear charge, therefore more ionization energy. Phosphorus versus silicon, the same shielding in all these three, but all these three the nuclear charge is increasing, so again they go back to increasing the ionization energies. But then you got sulfur. Why is that decreasing? Because between phosphorus and sulfur, the difference is that in phosphorus and in silicon and in aluminum, these outermost are occupying the orbitals singly, while in sulfur the fourth electron that comes in the 3p starts to pair up, and when it's pairing up it's in the same orbital space, and these two have the same charge, negative, so they start repelling each other. In addition to the attraction, there is repulsion because they're occupying the same space. Now because of the additional repulsion, it becomes slightly easier to lose this electron versus any of these because they are not being repelled in the same space. Hence the energy required, and also that's why that repulsion will overcome the additional attraction by the 16 plus. So which is what makes sulfur's ionization energy a little lower than that of phosphorus's. The same thing is seen for nitrogen and oxygen, because nitrogen का outermost electron का configuration is 2p3 and oxygen is 2p4. And if you look at oxygen's electronic and shell diagram, is that there's in one orbital there are two electrons, and this inter-electronic repulsion, the same orbital space, causes this to be less attracted, therefore easier to remove, versus nitrogen, the guy before it, because they have 7 protons and 8 protons, 15 protons, 16 protons, more attraction but overcome by more repulsion because of the same orbital having 2 electrons. Repulsion easier to lose versus phosphorus. But then chlorine has the same problem as sulfur, so between the two of them they both have inter-electronic repulsion, but chlorine has a greater charge now. So in दोनों में सिर्फ फर्क है, chlorine का nuclear charge ज़्यादा है, therefore again it goes back to require more energy. So the underlying theme across this whole is that every consecutive member has a greater nuclear charge, and if nothing else changes from that and the previous guy, then the nuclear charge will pull the electron more and require more energy to be lost. But the two hiccups are happening from group 2 to group 3 because the group 3 element, the outermost electron, will occupy an p orbital, which in addition to the previous shells also is shielded by the same shell's s orbital, versus the group 2's, which doesn't have that problem. So the group 3 takes a dip, then it goes rising again because the only change is nuclear charge, and nuclear charge increases ionization energy. Then there's a dip from group 5 to group 6 or group 15 to group 16, because in group 15 or 5 the electrons are singly filled like the previous guys, but in group 16 they start to pair up. When they pair up, the repulsion increases, easier to be lost. Repulsion increases, but between chlorine and sulfur, chlorine has a greater nuclear charge, so therefore that's why it starts to rise again. So what the exam will do is ask you for a general trend, and you'll say the general trend of period 3 ionization energies is that they increase because the nuclear charge increases, the shielding remains almost the same, therefore first ionization energy increases. Then they'll ask you specifically, okay, so why is aluminums less than magnesiums if they're supposed to increase? And the reason is, in aluminum the electron is occupying a 3p orbital, and in addition to the same shielding as before, it also has additional shielding from the 3s electrons, hence it takes a dip. Also, why is there a dip for sulfur versus phosphorus? Because in sulfur the electron is pairing up, finally begins to pair up, and that pairing up increases repulsion, easier to lose, versus the previous guy where there is no repulsion. So that's where the two dips exist, and you got to remember that. And yeah, so that's the wrap for this chapter.